Modern researchers have access to massive amounts of predictive data. We can track clicks, forecast demand, and measure engagement down to the millisecond. But forecasting an outcome is entirely different from understanding the underlying mechanisms that drive it. Prediction does not equal explanation. In rigorous research, explanation is the sine qua non, the essential condition for scientific progress. Without it, you only have mere observations. Formally, an explanation is a systematically structured argument. It demonstrates logically that a specific phenomenon was scientifically expected to occur. There is a sharp divide between noticing that an event happens and proving it had to happen. The latter requires linking specific antecedent conditions, the actual circumstances of the situation, to covering laws that dictate the outcome. When strategists rely on predictive models without explanatory structures, they are trading on blind correlations. As soon as the market shifts, those correlations break down, leaving them entirely vulnerable. To qualify as a valid scientific explanation, any theoretical model must survive 4 strict epistemological filters. The first is expectation. The model must predict the phenomenon. The second is pragmatism. The model has to align with actual scientific practice rather than abstract theory. The third filter is intersubjective certifiability. A model must be testable and verifiable by independent outside researchers. This strips away pure subjectivity and ensures the findings rely on evidence, not personal bias. Finally, a valid model requires empirical content. It must be rooted in the observable world. We have to rule out purely analytic statements, like circular definitions, where A equals B because B equals A. Any framework failing these 4 criteria falls into the realm of pseudoscience. These strict standards set the baseline for evaluating the dominant models in the philosophy of science, starting with logical empiricism. The bedrock of logical empiricism is the deductive argument schema. This diagram shows the explanans, a combination of specific conditions and universal laws. Together, they form a rigid premise that deductively implies the explanandum, the phenomenon we are trying to explain. The classic example is the deductive nomological, or DN model. If we want to explain why an ice cube floats, we define the conditions of the ice and the water, and we invoke Archimedes' principle and Newton's first law. The outcome is a guaranteed deduction. In practice, researchers often use an enthymeme. This is an elliptical explanation where they deliberately omit stating obvious universal laws, like Newton's, for the sake of brevity. This deductive certainty also applies to probability in the deductive statistical, or DS model. Here, statistical laws are deduced strictly and mathematically from other established statistical laws. If we know a supplier has a 50% probability of securing a single order, we can deduce with mathematical certainty that the probability of getting 2 orders in succession is precisely 25%. Because these models are rigidly deductive, they are strictly falsifiable. Looking at this text from modern marketing theory, test 1 shows that if the logic is sound and the expected real-world outcome is false, the entire DN model is definitively false. DN and DS models offer perfect logical certainty, but because they require strictly universal laws, they are exceedingly rare in the messy, variable reality of the social sciences and marketing. For the social sciences, researchers default to the inductive statistical, or IS model. As we see here, the solid deductive line fractures.
The laws in this model do not guarantee an outcome. They only confer a degree of likelihood. This creates critical vulnerabilities. The first is weak falsificability. In test 1 for the IS model, a single counter instance does not destroy the premise. Because the laws are statistical, an unexpected outcome merely renders the model not supported. The second flaw is the mathematical difficulty of quantifying exact inductive support. When dealing with complex overlapping premises in human behavior, determining precise statistical likelihood becomes incredibly murky. The third vulnerability is inductive ambiguity. Philosophers illustrate this with the paradox of Jones, a man who is both Scottish and an American Southerner. We have 2 perfectly true statistical premises. Scots are highly likely to drink Scotch, and American Southerners are highly unlikely to do so. Within the exact same framework, these valid premises lead to contradictory conclusions about what Jones will drink.
The philosopher Karl Hempel resolved this paradox by demanding maximal specificity. These explanations must be based on the most narrowly defined, relevant reference class possible to avoid competing probabilities. Because the IS model lacks the bulletproof certainty of strict deduction, marketing researchers must exercise extreme rigor. Defining precise reference classes is the only way to protect inductive models from contradictory logic. Even perfect deductive logic has blind spots. A famous philosophical thought experiment exposes why predictive power alone is insufficient for science. This is the flagpole counterexample. If you know a flagpole's shadow length and the sun's angle, basic geometry perfectly deduces its vertical height. The predictive math is flawless. But the shadow's length absolutely does not explain why the pole was built to that height. Predictive adequacy fails utterly without an underlying causal mechanism. A shadow cannot cause a flagpole. To truly explain an event, the cause must precede the effect. This paradox mandates a philosophical approach called scientific realism. Realism dictates that valid explanatory models must include actual physical entities with genuine causal powers, rather than just mathematical correlations. Marketing analysts frequently act like the person measuring the shadow. They celebrate a predictive data correlation while remaining entirely ignorant of the fundamental causal mechanics actually driving the market behavior. The inductive statistical model faces another severe challenge regarding causation. Wesley Salmon introduced the statistical relevance, or SR challenge, attacking the requirement that an outcome must be highly likely to be scientifically explained. Salmon argued causality exists independently of high probability. This diagram illustrates two medical realities. Smoking causes lung cancer, and penicillin causes rashes. Although the condition occurs in a small minority, the low probability event undeniably demonstrates cause and effect, breaking the high likelihood rule. Shelby D. Hunt resolved this philosophical stalemate by redefining the role of statistical relevance in theory generation. Hunt argued that SR models are effective at identifying relevant variables and correlations, but they serve only as intermediate steps in the research process, not as final, conclusive explanations. To generate genuine theory, an explanation cannot stop at statistical relevance. It must eventually graduate back to an IS or DN structure that is firmly grounded in a realist, causal view of the world. Some researchers attempt to bypass mathematical constraints by using the pattern model. This alternative framework attempts to explain a phenomenon simply by fitting it into a recognizable, pre-existing narrative pattern. Abraham Kaplan illustrated the flaw in this approach with a simple visual. If you watch a soldier walking a dog pass behind a solid building, you might only see a generic stick-like shape trailing behind. The pattern model relies on the observer to fill in the missing data based on assumptions. Because of this, it fails the intersubjective certifiability criterion. Cognitive bias ruins the reliability of the model. One researcher might confidently classify the trailing shape as a dog's tail, while another independent researcher classifies it as a dead tree branch. There is no objective way to resolve the dispute. The pattern model is strictly relegated to the context of discovery. It is useful for brainstorming and hypothesis generation, but it is explicitly banned from the rigorous context of justification required to prove a marketing theory. Another common approach in the social sciences is the functionalist model. This is a teleological framework that explains an institution's behavior based on its contribution to the survival of a larger system. Functionalism initially suffers from a teleological paradox, implying that a future goal causes present action. The resolution is that the future outcome does not cause the action. Rather, the current desire for that future outcome is the causal mechanism. Basic functionalism, known as Functional Model 1, assumes a rigid, linear flow. This diagram maps the logic. A system need dictates a specific, indispensable behavior, which leads to system survival. This framework contains a fatal formal invalidity. It commits the logical fallacy of affirming the consequent. It falsely assumes that because the system survived, that single specific behavior was the only possible way it could have survived. To save functionalism from logical collapse, researchers must rely on a revised structure known as Functional Model 2. It rescues the logic by introducing the concept of functional equivalence. It acknowledges that multiple, entirely different behaviors could fulfill the exact same system need. Advancing marketing theory requires abandoning subjective patterns and logical fallacies. Scientific progress demands objective, causal, and structurally rigorous frameworks that move beyond predictive data to provide an actual understanding of market mechanics.